我叫米老师, as Zhang Wei said, and today we are in our fourth week of the science writing class in English and for Impact. And this week, called Tricks, is going to be a mixed bag. It's some things that didn't quite fit into the week on philosophy or the week on structure or the week on strategy. So there are some elements of philosophy, structure, and strategy in today's talk. The common theme today is really from small things to big things. There are tricks of the trade. Experiences that I have learned on my own and experiences that I have learned from my professors to how to write a paper from beginning to end. So last week with strategy, we focused a lot on, the review aspect, kind of the end and revision, the end of a publication process. This week will be a little bit more about how the process even begins. So in the structure, we talked about kind of the middle of the process. We'll talk about how to come up with ideas even today. So a couple tricks on all the topics we've covered and some new stuff. 好的，开始吧。I do need to always start by thanking the mutual encouragement from Wu Fuyan 老师, Peng Peng 老师, and Zhao Liang 老师. The three of them are the reason why this lecture series exists. Gongmian, mutual encouragement, something I'll talk about today in science, was critical. And Peng Peng 老师 and I have been working together for many, many years. Here we are as young men in Canada, doing some field work and enjoying some coffee. And thanks to all of you, okay? Since we started recording the videos, I've even been getting feedback not only the day after the presentations, but throughout the week. So many of you, as Zhang Wei said, many of you have given feedback, and that's invaluable. Okay, so whether you email me or Wishing, I really appreciate the feedback, whether it's something you liked or whether it's something you haven't heard yet, or whether it's something you would like to hear more about. It's all good. So as I said, this has been the structure of the lectures. Week 1 about philosophy, very general ways to improve your writing. Week 2, structure, specific ways to improve your writing. Strategy, big things for big journals. We talked about cover letters, decision letters. Today, tricks, little things that make a big difference. And next week, Wu will be, in my opinion, the most important week. I have received amazing feedback from many of you. I have been keeping a list of the things you found useful and the things you would like to hear more about. So next week, the final week, will be all about you. So please, if you haven't already, or even if you have, please give me some feedback or more feedback soon so I can continue to structure the last lecture together. And just remember this very important metaphor of the whole process of science being like a climb of Mount Everest in Tibet. Do not underestimate how much of science is writing. As students, we learn a lot of things, but rarely writing. But your career depends on your ability to write. And what percentage of the process is writing, I would ask you? I would claim that surprisingly large, and most importantly, writing is the last critical step. So from base camp up to camp 1 with your field work and your lab work gets you your data, which you have to analyze. But really everything, immediately before camp 2 and after camp 2 is writing. Writing the first draft, revising the second, third, fourth, fifth draft, Then you get the reviews back. And then you have to deal with the revision process that we talked a lot about. So never forget why we're talking so much about writing in science. And as I've said before, take it or leave it. This is my advice from my personal perspective. What works for me may not work for you. Everyone needs to find his or her own style and approach. Some advice may be helpful. 他帮了. Some advice may not be helpful. 没问题. You will benefit no matter what from thinking about the process. Sometimes I will give two different approaches. Maybe you prefer one over the other. Maybe one works for one paper and the other for another paper. So take it or leave it. Most importantly, think critically yourself. Now, before we get into specific tricks, before we get tricky, let's be clear about the most important thing we're talking about here, authorship. What is authorship and what isn't? There is only one criterion, not multiple criteria. There is only one criterion for authorship, and that's intellectual contribution. There's nothing else. So start practicing intellectual contribution now. It will help you for your papers and for co-authorship papers. Now, there are many ways to make an intellectual contribution. You can come up with the concept, the idea. Often this is done by your advisors. You can develop the concept. Once you have the data, you can help with the interpretation. You can test a concept by doing the data analysis, and farther along, you can articulate the concept. That's in the writing, that's in drafting of the figures. Now, none of those things I said that constitute authorship, none of them, those things do not include things like providing funding, providing a sample, helping with field assistance, or routine lab work. Now, those last two things, assisting someone in the field or doing some lab work for someone, these require interpretation. In some cases, it merely involves acknowledgement. In other cases, if you are making an intellectual contribution, then assisting someone in the field or doing lab work that's quite technical or involves very careful thinking, that may constitute an intellectual contribution. Main point is that keeping this goal in mind, this goal of making an intellectual contribution, keeping this goal in mind will help your mind reach the goal more often. Okay, so always keep this in the back of your mind. Now let's get tricky. Little tricks that can make a big difference. So, last night I had a very, very bad wine. The front of the bottle, the label looked very nice. It was from France. The price seemed like it should be good, but I didn't read the label on the back. And after tasting the wine, I read the label on the back, and I won't read it out because you can see yourself why I should have known better. So between the words the and latest, they're missing a space. They have words that are broken up from line to line. And then at the bottom line, there's a period in the middle of a sentence. And then in the second to last line, there, for some reason, there's a space, a line break in the middle of a sentence. So based on the number of errors in punctuation, grammar, and even logic, if you read the phrase, I should have known this wine was going to be a bad wine. And what do I mean? How, why does this label matter so much? Well, presentation matters. And think of your paper like this bottle of wine. Presentation matters. First impressions matter. You can't get a first impression back, so make it a good one. Little mistakes might not seem important. They're not the science part of your paper, but they can add up in a bad way. Examples such as misspellings. Okay, I know with your writing in English, you probably turn spell check off because you have so many errors that you don't want to be distracted by all the misspellings. I understand that, but after you finish a draft, please turn spell check back on, because if a reviewer sees a couple, only takes a couple misspellings, they can give the editor the impression that you're not very serious. Other examples are inconsistencies in terms. If you use a term once and you capitalize it and you use it again and you don't capitalize it, little things like that are just distractions from understanding the science. And formatting being wrong for a journal. It's a big sign of respect if you have the right format. If you get rejected from Nature and you submit it to Science with the formatting, not only are they going to know that, it just shows a lack of respect for the journal, for the editors. And something we talked about last week, bad figures, okay? Figures are not just about portraying, showing the data. It's about being understood and being compelling. So we talked about this last week. Make nice figures. Pictures, a pretty picture the importance of a pretty picture cannot be understated. And then there's more examples. The general principle is dress for success. Just like how you would dress up for a job interview, your paper needs to be presentable if you want your paper to be taken seriously. And a couple more little tricks. We'll get to the bigger ones next. But here's just a couple more little tricks that make a big difference. Your discussion section needs to start with a strong first sentence. This is your conceptual advance. If you can't write this one sentence, you're really not ready to write the rest of the discussion. But once you have that first sentence, then you're on your way. When using abbreviations, don't forget grammar. Scientists use a lot of abbreviations, but remember that abbreviations are taking the place of words, and words have grammatical requirements. So a couple examples of punctuation is missing when people use abbreviations. There's the abbreviation EG, which means for example, and there's the abbreviation IE, which means in other words. Both of these abbreviations, if you were writing them out in long form, both of them would be followed by, preceded and followed by commas. Very often people put the comma before, but they don't put the comma after. So that's just an example where punctuation needs to be involved in abbreviations. And then often people make mistakes of singular versus plural nouns when they use abbreviations. So the example here is LREE. Even though this means light rare earth elements, plural, many times people don't put the little s, which is fine. It's a plural abbreviation. But that means if you write a sentence, you should not say LREE crystallizes. It needs to be LREE crystallize. If it's a plural abbreviation, the grammar, the verb needs to reflect the plural agreement, subject-verb agreement. Commas, I see a lot of mistakes in writing where there aren't commas where there should be, or there are commas when there shouldn't be. There are many strict rules for grammatical rules for commas. I know some of them. I don't know all of them, but my advisor, postdoc advisor, Joe Kirschvink, told me one of the best things. Try reading your sentence out loud. Commas are where pauses exist, okay? So you don't have to know all the rules. Just try reading it out loud. And when you find yourself taking a pause, comma, there should be a comma. The words which versus that. Just simple rule. If you use the word which, that should be, there should be a comma before it. If you use the word that, there should be no comma, okay? And another simple example, if you have ranges between X and Y, if you say from X and Y, you can use a dash. If you say between X and Y, you need to say spell out and, okay? And the trick to remembering this is that from is a shorter word than between. So you use the dash for from and spell out and for between. But let's get to the more exciting tricks. Web of knowledge. Your main job as a scientist is to keep on learning. You've learned all your life as a student, and that job of the past is also the future of your career. And as you learn about what is known, you will begin to learn about what is unknown. So learning is obviously an important thing to do, right? And I think of learning like a spider web or any kind of network, connected network. If you are trying to learn something new, you must try and connect it to something or some things you already know well. This way, you will connect with these new concepts. If you connect it to something you already know, you will remember it. And in fact, this is what you're actually doing in your brain. You're actually connecting the pathways of your neurons. You're literally making these connections in your brain. So that should be the way you think of it. And in this process, most excitingly, you can sometimes even make a creative connection that no one else has made before. And in doing so, you might find a new idea. Everyone has their own web of knowledge. And literally what new ideas are is when you make a connection in your personal web of knowledge that other people haven't. And when they hear it, they're going to update their web of knowledge. A lot of metaphors today, lots of analogies. Science is a staircase. I know all of you know the phrase from Isaac Newton, "If I have seen further, it is by standing on the shoulders of giants." Science is a staircase. It advances one step at a time. Of course, some steps are bigger than others, but still, concept we talked about last week, one idea, one paper, or one paper, one idea. And the best way to come up with a new idea is to both understand and really appreciate the ideas that have come before you. And this means don't just read the recent papers, not just the papers, oh, these are the most up to date. Also read the classic papers that those recent papers cite, the papers from the 1960s and the 1970s, 1980s that are still getting cited today. In the lower right-hand corner, I show a histogram that has a positive skewed distribution. Think of this as a classic paper that obviously has most of its citations when it first comes out. It reaches a peak, and it obviously diminishes over time. But many papers stop getting cited, and some papers continue to be cited. And those are the papers at the bottom of the staircase. They're still part of the staircase. If you are learning about science step by step, you are smart to go back to those old papers because those are the papers that your advisors read to come to their understanding. And sometimes reading something out of date is also a good practice for your brain, where you can identify, oh, that is still true, but there's something that isn't true. So it's a good way to start thinking critically about great papers. And another analogy that one of my advisors shared with me, I'm sorry if these aren't popular in China, but you may have seen a crossword puzzle before. These are words, there are words across and words going down. And those across and those downs, they intersect. And if you have solved the puzzle right, you're given clues to all the acrosses and all the downs. If you have solved the puzzle correctly, if you have the across and the downs both right, then they should agree with each other. And what do I mean when I say science is a crossword puzzle? We are all experts in one method or another, and we're often working on the same problem, but approaching that problem from different angles. For example, data and theory should be compatible with each other, just like the vertical and the horizontal words in this puzzle. And if there isn't agreement between the across and the down, then something's got to give, something's got to change. One or the other has to be wrong. And this is a great, I offer this analogy because I think it's a great way to come up with new ideas. And being aware of these intersections, however, it really requires doing reading outside your expertise. So I'm an expert in paleomagnetism, okay? And I can know all of the horizontal, all the across. I know this paleomag, I know this paleomag, I know this paleomag constraint, but those constraints are solving problems about supercontinents, for example, that the geological record or the geochemical record also have vertical constraints. So I can actually test my idea about paleomag by being aware of geological and geochronological constraints, just as an example. We talked about this principle in the, I think it was the second week, but I bring it back because it is really one of the most basic tricks that really improves your writing. Economy of words. What do I mean? Is delete every unnecessary word. Every big scientist I've ever worked with, Sam Bowering, Joe Kirschvink, they would edit my manuscripts always reducing the number of words. Why? Every word matters. There's a reason why science, nature papers, geology are short. It's not just because they have limited space. It's because it leads to better writing. And this is the example I gave last time. I just want to give another example. This doesn't necessarily mean shorter sentences, okay? Long sentences should obviously be avoided, but in this example, I'll show you why a long sentence is actually better. It says, seismic studies in adjacent regions to the north and the south revealed a flat moho at 40 kilometers depth, period. This suggests that, da, 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 da. The problem, so what I've done in the modified version is I just put a comma and said, instead of this suggests, just saying suggesting that. And this is better for several reasons. First of all, there's one less word, but really it avoids the ambiguity of the second sentence. You should never say this suggests. If you ever say this, it should be followed by an actual noun, not just the pronoun, the ambiguous pronoun of this, this feature or this connection, okay? And this is a neat principle that it's a trick that will improve not only your writing, but also your thinking about the science. And it's something I learned from Adam Malouf, now a Princeton professor, who always wears these red suspenders at every geological meeting. Authors, science, not scientists. When you're writing, authors don't exist, just their ideas. For example, you could write Lee et al. 2008 reconstructed Rodinia, ... I don't like that. What do I like? The first global reconstruction of Rodinia, Lee et al. 2008, in parentheses. Why is that better? Well, it's describing the nature, the process, not the people. And in this example, we obviously know someone reconstructed Rodinia, and that person will be given credit in the parentheses. But by saying the first global reconstruction of Rodinia, we're actually learning something about that reconstruction, not simply who did it. So this is really the best thing about this is if you don't focus on the people, you start focusing on the process and nature itself, which is really what you're writing about. And it helps you go straight to the state of the art. And as you do this in your writing, it will require you to think more on how different contributions relate to each other. You can't just say, this author did this, then this person did this. You actually have to talk about these different contributions and how they're related in terms of understanding nature. Now, there is an exception when you're discussing the historical development of knowledge, but this is often very, very limited, and really you should avoid it if possible, okay? And this brings me to another related point, the last one, that literature should be discussed in the present tense. Even if an old paper is old, I can still read it today. Okay, so instead of saying Lee et al. Suggested, say Lee et al. Suggest. Okay, so focus on the science, not the people, and talk about the literature as it exists as a body of present day knowledge. Now we're moving through the review process, and you submitted your paper. Submit it and forget it. Submit it and forget it. After submitting a paper, it is out of your hands. You have released the bird into the wild. Do not check the status of your paper every day. If the paper goes to review, you will know within 1 or 2 weeks. Either you will be emailed or you only need to check once or twice. Okay? If you do check every day, your mind is preoccupied with something over which you have no control. So focus on what you do have control over. Free your mind for the next task. Remember from past lectures, the juggling analogy we used. You have no control over the balls in the air. Okay, so just focus on catching the one that's coming back and throwing the next one. And when you submit a paper, it's in the air. Time to get another ball in the air. 2 things: get another ball in the air or get ready for another one to have the revisions. And why do I really say this also is revision process takes a lot of time and effort. So use the time after submission of one paper to work on the next or other tasks. And then there are other things other than writing papers: funding proposals, lab work, field work, collaborations, busy work. You all know this. Submit it and forget it. Lots of analogies today. This is about the review process. We have a phrase, I'm sure there's a good Chinese idiomatic expression for this idea as well. We say, kill 2 birds with 1 stone, okay? And this is about revisions. This is a critical principle for revisions. You read all the reviews, 1, 2, 3 reviews, and figure out if making one change to your paper can address comments from maybe 2 or even more reviewers. And how do you do this? You do this by finding the common themes in different reviews, a similar concept that came up, maybe in different ways, but the general concept was in 2 or more reviews. And if you do find this one change that can address multiple comments, this is a more efficient use of your time. Less changes are needed to be made in your revision. And this also comes across to the editor like you found a very elegant solution to the reviewer comments without changing your idea too much. They sent the paper to review the first time. They liked your first paper. You obviously need to change it to make it better, but if you change it too much, the editor might be worried and send it out to new reviewers. And how you address the 2 or 3 themes can be briefly summarized for the editor in the cover letter. We talked about that last week. So, in those bullet point form or one paragraph about the different reviewers or the different problems, this is where killing 2 birds with 1 stone really helps the editor understand very quickly how you responded to the reviews. And it avoids this problem of death by 1,000 cuts. Reviewers, using lots and lots of words, a very long review to essentially keep saying the same thing over and over again, but in different phrases. So if a reviewer had 20 comments, maybe 8 of those comments were actually about one theme or one concept. And if you address that, if you kill 8 birds with 1 stone, that's great. Now, the next 2 slides about collaborations, and this is something it's probably less important to you as a student, but if you're going to be a successful scientist for a career, you absolutely need to develop the ability to collaborate with more people than just, say, your supervisor. So, like anything that you need to develop and evolve, it's always good to get even a little practice as a student, definitely as a postdoc, and certainly as a young professor. So the Beatles, my mother's favorite band, they have this great phrase: "The love you take is equal to the love you make." Very similar to the concept of gongmian. You get what you give. I understand the importance of first author papers in China, and I'll talk about that a little bit next slide. But even though first author papers are very important, do not view time you spend helping other people on their papers as a waste of time. We've talked about how we learn best by mimicking, imitating others, and also by comparing ourselves to others. Okay. If a colleague, one of your classmates publishes a paper, if you help them in the process by comparing your thinking to their thinking, you're learning. When you help someone else, you help yourself. Not always as a co-author, but sometimes as an acknowledgement. It really just depends whether you made an intellectual contribution. And there's a great Chinese phrase that my colleague and friend Yang Wei Lao Shi shared with me: ask about the cultivation, not the harvest. You don't want to leave discussions about authorship completely to the end. But if you're just helping someone and you aren't clear that you're going to make an intellectual contribution, don't start talking about authorship. But as soon as you do, you can worry about the harvest. Okay. And, obviously, I am, been working for many, many years now. And one of the things I love about IGG are the many different people with whom I get to work. Here's basically just a short list of some of the many of you that I've gotten to work with. And I make this list mainly as a thanks, because I have learned so much the last 2 years from so many of you. And I also want to give an example of my own career, because that's what I know. And if I'm being honest, there's been an evolution throughout my career between first authorships and co-authorships. So first authorships and co-authorships are both important to have. First authorships give you more control of the science, but co-authorships give you more influence. You're able to work on more than just the things that you are first author on. And you build a network of collaborators. But I want to point out how my career and your career will evolve. Yours might be different, but it seems like it would be similar. So you'll know the ones in bold are ones I'm first author on. And in the very beginning, in my first 12 papers, I had very, very few co-authorships, okay? That makes sense when you're a student and a young postdoc. But then when I went to Curtin University in Australia with Li Jianxiang, Lao Shi, I joined a large group, a multidisciplinary group. And that was a real opportunity for me to work on being a co-author. And so then actually, during my 3 years at Curtin, I actually only had 3 first authorships at the same time that I doubled my publication list. So you want quantity and you want quality. And so as a student in postdoc, I learned the importance of first authorships. Then as a research fellow with Li Jianxiang and his group, I learned the importance of co-authorships. And then coming to China in IGG specifically, I was able to do both those things. So just like Curtin, in my first 2 years here, I've doubled the number of publications, but also because China values first authorships, which I needed for promotion, I also had to go back to what I was very good at as a student, and that was writing the first authorships. So you need both. And it took me a long time to develop both of them. But for those of you that want to become postdocs and professors, just keep in mind that this is a development you'll have to start. And obviously, thank you, IGG. It's a very good fit for me. Now, this is probably the most important thing, that is the hardest thing, that is also the hardest thing to teach. Ideation, the production of ideas. How do you come up with a Nature Index level idea? It's hard to teach because it's even hard to know how one comes up with ideas. But since the feedback I've received from many of you is about this interesting idea of ideation, the production of ideas, I'm going to try my best. And I think the best way is to just give examples. So today, I'm going to, in our last 15 minutes, I'm going to talk about how I came up with, I think, the idea for my Nature paper. And next week, I'll try to come up with a couple more examples, because there are obviously more than one way to come up with a top idea. But as I've worked these examples up, I've also noticed that there are some common tricks, common themes. So the example today was obviously the most important chapter of my thesis. Interestingly, it wasn't originally at all part of my thesis, but the preparation I had done in paleomagnetism in deep time, in the Precambrian time, the preparation I had done completely prepared me for potentially developing a nature level, nature index level idea. And so here's the story. And I just point out that there's 3 authors on this paper. The third author is my advisor. And the second author was a really close friend and a peer. And don't just learn from your supervisors, learn from your peers. There are things, you can talk to them more often. You can share your problems with them more easily. So use your peers, use your friends and your fellow students as much as you do learn from your supervisors. So this is the basic idea. I'm not going to go into all the details, but just so you appreciate what the idea is and how it came to be. On the left, in panels A and B, these were the previous models for how supercontinents like Pangaea form. So we're looking at the globe as the continents are today, looking down from the North Pole. And the introversion idea in A was the idea that the Atlantic Ocean opens up, and then the next supercontinent will form by closing the Atlantic. The extroversion idea was the idea that the Atlantic Ocean opens up and it's going to continue opening, opening, opening. And in doing that, it will close the exterior ocean, the Pacific. So the old ideas were all about the oceans. You open the Atlantic and close it. You open the Atlantic and close the Pacific. They were purely geometrical in concept. And then our idea, which I really share with my advisor, I gave it the name, and well, I'll talk about what I did. But this new idea, orthoversion, was related not just to geometry, but also geodynamics. And what I mean by that is how mantle convection occurs on Earth. So those yellow regions, okay, is where the mantle is upwelling, okay? And the blue region in between, the ring of fire today, where all earthquakes and volcanoes occur, that's where the mantle is downwelling. And just thinking about how continents drift, they typically want to go flow downhill, and they don't want to flow uphill. So the basic idea was, instead of closing the Atlantic, instead of closing the Pacific, no, the supercontinent is going to be halfway in between those other models. So introversion was 0 degrees. The next supercontinent is going to be the same as the last. Extroversion was 180 degrees. The next supercontinent will be positioned 100 on the opposite side of the Earth than the last one. And this idea, orthoversion, ortho meaning 90, orthogonal angle, 90 degrees. This idea was not 0 degrees, 180 degrees. It was in the middle, 90 degrees. And where did the idea come from? Well, it came from me reading my advisor's papers. This very good paper of his, True Polar Wander and Supercontinents. Those are the 2 important concepts that I ended up linking together, as you'll see. So what my advice is, read your papers, read your advisor's papers in detail. You can admire their work, but also think critically about their work. And as we said, you stand on the shoulders of giants, but your job is to take the next step for science, okay? So let's get specific. What was in his paper that inspired me? I should also mention that even before I read this specific paper, I had motivation that came from understanding a very basic problem in paleomagnetic reconstructions of supercontinents. And the problem is that when a supercontinent breaks up and all the continents get scattered, there is no reference frame in which to reconstruct the continents. So just in the back of my mind, even before this current paper, I had already wondered, is there any way to link one supercontinent to the next when the continents get all scattered in between? Is there any reference frame that we can find that links those two supercontinent cycles together? And here was his important figure. And I noticed a systematic pattern in the way he drew his figure. So you'll see in panel B, okay, he has the supercontinent sitting on the equator right before breakup. And then in panel C, the continents break up, okay? And then they collide in this gray band, okay? This gray band is the same thing as this blue band. This is where the mantle is downwelling, okay? So in his figure, he had the new supercontinent forming at a 90-degree angle from where the previous supercontinent had been. If you look at the previous supercontinent in panel B and the new supercontinent in panel D, they are 90 degrees shifted in longitude. And that was the idea from the figure. And then I went to the text. What in the text did he say about this? Well, and I read specifically on the top right, the model described below, following Evans 98, his own paper, also incorporates a two closed cell configuration, but one that shifts its axis relative to the mantle by about 90 degrees with the maturation of each new supercontinent. So I thought, wow, what I saw in his figure is confirmed in the text. And you found this prophetic sentence, this sentence that would inspire our work together. And it's okay to like a hypothesis as long as you love to test it, okay? You know, some scientists think you have to be impartial or skeptical. You know, enthusiasm isn't different from being skeptical. And what did I do? I thought of a way to test it. And I couldn't believe it. When I talked to my advisor about this idea, he had just assumed that there was no way that this 90-degree shift could be tested. But as I said, preparing for my thesis, I had been looking at the paleomagnetic data and I had been seeing some patterns in the paleomagnetic data that I thought could be used to test his idea. And how did we test it? I don't want to get too technical, but we used this process called true polar wander. So you remember in his paper, there were two concepts, supercontinents and true polar wander. What I was going to do is I was going to use true polar wander to help solve the supercontinents problem. So what is true polar wander? As you see in the picture, what it would look like if true polar wander happened today, it's the wholesale shifting of the shifting of the solid Earth. Okay, so Earth is rotating, but it moves its mass around because of plate tectonics. And as the continents shift and the mantle convects and these masses move, Earth actually wants to find a new axis to spin around. So if we're looking at Earth from space, this is what it looks like. Earth is tipping and it's rotating around this axis on the equator. Now, how does that help solve the supercontinent model problem? Well, True Polar Wander to the rescue. In my mind, we have True Polar Wander occurring around an axis in panel B for the first supercontinent, okay? And then when the new supercontinent forms, if this idea of 90 degrees is correct, okay, then the new supercontinent will form 90 degrees away. Eventually, it will end up on the equator like Pangaea. And then its own axis of True Polar Wander will be different from the one before it. So Earth used to wobble around this axis, and now it will wobble around another axis with a 90-degree difference in longitude. So what we had to do was find evidence of TPW, True Polar Wander, from two successive supercontinents and compare them. You measure the red axis and of the one supercontinent and measure the red axis of the other supercontinent based on the data, and you measure the distance between those two axes. And if the idea of 90 degrees, if orthoversion is correct, the angle between the two axes should be 90 degrees. And I remember running to his office when I made this first plot. So there's the data in blue from the young supercontinent Pangaea. When Pangaea had True Polar Wander, it wobbled back and forth. And then there was data from the southern part of Pangaea, Gondwana, that was older. And that was left over from the previous supercontinent, okay? And what we found was the data oscillated in one plane with an axis in blue, and then it oscillated in another plane with axes in orange and green. And when we measure the distance between the blue and the orange and the green, we're measuring the distance between the True Polar Wander axes. It was almost exactly 90 degrees. It was 87 degrees. And he's looking at the figure, and oh, that worked out well. And why didn't you do this yourself? And he said, I just assumed we couldn't do it. So we had our first success, and then he continued to be skeptical. Even though this was originally his idea, and I had found a way to test it and prove it, he was still skeptical, and he said, hold on, we don't just have two supercontinents, we have at least three supercontinents, so we can do not only a comparison between these two, we can do a comparison between these two. We have two opportunities to do a test. So of course, I already had in mind the data because I was prepared for my thesis. And then that night, I plotted the next comparison between the two older supercontinents. And again, the data from one supercontinent in orange oscillated in one plane with an axis in orange, and the data from another supercontinent oscillated in another plane with an axis in red. And if we measured the distance between one True Polar Wander axis and another True Polar Wander axis, we found 90 degrees. So, to come back to this idea of science as a crossword puzzle, what happened here? My advisor had come up with a conceptual idea of the supercontinent cycle. And what I did was I found a way to test it with paleomagnetic data. And just like our crossword puzzle, his conceptual model The theory, okay, is the horizontal word, and the data was the vertical word. And what we found was a compatibility, that his constraint and my data analysis were consistent with each other. So the main lesson that I didn't put in here that I should have emphasized, though, was that sometimes your preparation it prepares you for coming up with an idea, but you'll never have that idea if you don't read the papers and prepare your mind about the problems. Okay. My mind was already thinking about how to connect one supercontinent to the other supercontinent because we had this problem of the continents breaking up, getting scattered. Finding that we had a link from one true polar wander axis and the next true polar wander axis, and we can just assume that it's 90 degrees. This allowed us to solve the problem that I had been worrying about. So it was a combination of preparation, knowing the problems in your field, and reading my advisor's paper critically. So that was just one example. It was helpful for me. I hope it was helpful for you. Next week, since this is a question that has come up from several of you, I'm going to try to give one or maybe two more examples of some of these Nature Index level papers and how their ideas came to be. So thank you, 谢谢, and 加油. Remember, practice makes perfect. So start enjoying your writing, and I look forward very much to sharing our last week together. It's been a lot of fun talking with you guys. 谢谢。